All right, so I'll just summarize what we have been talking about in the last class, right? So we started by saying that we can obtain all of special relativity by starting with the geometry given by d square is equal to c square dt square minus dx square minus dy square minus dz square, right? This geometry is known as the Minkowski geometry. Okay, and we saw that it's related to the proper time. We saw that d tau can be written as ds by c. Okay, it's related to the proper time. We said this is we called it as the space-time interval, right? Space-time interval. We called it as the space-time interval. So it's a notion of distance between 2 points in space-time, right? And we said we can draw space-time in this manner. We include a factor c over there so that the units are fine. All right. So we have got c, t, and x, supposing the other dimensions. So these points in space-time we called events. Points in space-time we call events. All right. And those are one more thing is so the trajectory in space-time we call the world line. The trajectory in space-time we call a world line. Okay, and the invariant distance, okay, distance between these two or any 2 points in space-time is known as the or a generalization of distance. It's known as the space-time interval, and it's given like so. Right, we said this is related to a proper time in this manner. Okay, and we looked at the invariance or symmetry transformations. We said that this is a geometric quantity, so it has to be invariant under certain kind of coordinate transformations. And we got back exactly the Lorentz transformation. Symmetry transformations are the Lorentz transformations. So, right, we wrote it in terms of hyperbolic functions, and then by we defined rapidity. Phi is equal to tan h inverse of v by c. We called it as the rapidity. Okay. Now we can write the Lorentz transformation either in terms of rapidity. Sometimes rapidity is more useful than the other things. All right. So we can either write it in terms of the rapidity or in terms of v by c or beta. All right, and it's exactly the same. Okay? So simply by starting with this, we got the transformations. All right, and we also got what we call as the time dilation. All right. And since this is related to the proper time, we said that proper time is relativistically invariant. Proper time is relativistically invariant. Okay, or it's Lorentz invariant. It does not change. Right. And what's proper time? We said proper time between two events. Right. The proper time interval between two events is the time elapsed on a clock. Okay, time elapsed on a clock which moves in a straight line in space-time, right, between these two events. All right. So you can ask what's the proper time between E1 and E2. What you have to do is that you take a clock from E1 to E2 along a straight line like that. All right. And the time elapsed on this clock will be the proper time interval between these two events. All right. Now, in this coordinate, right? So if you go to a coordinate system of this clock, which moves from E1 to E2, it's just the time elapsed on that clock, right? But from some other coordinate system, you will see that there are other factors involved, dt and dx. All right. In whichever way, this you can call as the coordinate time. Right? The coordinate time can be different. Okay, coordinate time can be different. The coordinate time is equal to the proper time only for this observer who is moving along a straight line between E1 and E2. All right. For other observers, there are other factors to be included. All right. So some people will say this is dt square minus dx square with the factor of c square there. Some observers will say it's just the time elapsed on my clock. All right. And all observers will agree on this particular combination. All right. All observers will agree on this particular combination. All right. This is called as the space-time interval or proper time. For this reason, we call it as the invariant interval. Invariant interval. Okay. So these are the things that we discussed, and we discussed the twin paradox, and we resolved the idea that there is no paradox there because special relativity predicts it only in one way. Okay. So we said we have got CTX. Okay, and one twin takes a straight line path between two events. Okay, their birthday, let's say 20th birthday. okay, straight line path, and the observer takes a different path. Okay, so obviously the distance, the time elapsed along these two paths are different, and that's the reason for the confusion. All right, there is no need for confusion. And we also mentioned this idea that the time elapsed along this trajectory. All right, the time elapsed between two events. Okay, we'll just time elapsed between two events. Okay, it's not generally equal to, right? It's not always equal to the difference in time coordinates of the endpoints. Okay. Okay, this means that if this point corresponds to time 1950 and this corresponds to a point 2020, okay, the time elapsed between these 2 points, all right, or these 2 points in space time, right, it's not always equal to 2020 minus 1950. All right, for one observer it is equal to 2020 minus 1950. That observer is at rest in this frame. All right, for other observers it's different. Okay, it depends on the path taken between these two events, and this is similar to what we do in space. Said this is similar to what we discussed in space, right? We can have 2 points in space. Now I'm talking about space. Okay, we can have a coordinate system, call this as x1 and x2, right? The distance between them, for one, the distance separation between them is x2 minus x1, all right? But the odometer reading is not x2 minus x1 for all observers, right? We can take a different path here. You'll see that for an observer who traveled along this path, it's greater than x2 minus x1. It's not x2 minus x1. This is not equal to x2 minus x1, right? It's in the same way. You have to consider time as a coordinate. You also have to learn to see time as just a coordinate. Once you change coordinate, you don't have the same thing again, right? So all observers don't call the same thing as time. So these are the things that we discussed in the last class. Okay. Is there any question?
Yes, sir.
All right, so we have time. All right, you can ask questions if you like. Now we already drew the space-time diagram. We were given a problem to draw the space-time diagram of these two twins, and we did it. Right, so but we'll go a little bit deeper into space-time diagrams. Okay, space-time diagram. So we'll just formalize whatever we have been talking about. So this is space-time. All right, this is space-time. Okay, and this is of a particular observer. All right, this coordinate system corresponds to a particular observer. We are choosing a coordinate system. All right? So we are now talking about this coordinate system. Again, as I said, there are world lines of particles. These are trajectories. This is the trajectory taken by a particle which is accelerating. All right, there are, if you are going at a constant speed, then you will have something like that, a straight line, but with a slope. Okay, these are called as world lines. Right, and for an observer who is at rest in this frame, the world line is just a straight line. Right, the world line is just the straight line, just a straight line parallel to a time axis. Now, if there's an observer who is at rest at the origin, his world line, this I want you to remember, right? His world line will coincide with the time axis. Am I right? This is the world line of an observer who is at the origin. This is also the time axis. Okay, so you see that the time axis is the same as the world line. Sorry. So one thing I want you to remember is the time axis, okay, of a coordinate system or of an observer. We also use the word observer, coordinate system, is the same as the world line of the observer at rest. Okay, at rest at x equal to 0. Right, at rest. Oh, it's actually at rest. It doesn't. So if you take some other point other than the origin, you'll get a straight line parallel to the t-axis. So that doesn't really matter. Okay, so we'll just say at rest. Okay, in the coordinate system. Okay, so if you want you can look at the world line of some other observer. You can look at the world line of some other observer. Okay, who is moving at a speed v like that. Okay, so if you are moving at a speed at a velocity, then you will have a straight line here, but with an angle with the x and t axes. Right? It will have a slope which can be determined from the velocity. The velocity determines the slope. Right? It's yeah. Yeah. So the time axis for this observer, this another observer over, the time axis for this observer would be his own world line. All right, the time axis of this observer would be the same world line. This is true. The time axis of a coordinate system is the world line of the observer at rest in the coordinate system. Right? That these are certain things. Okay, now right. Now, if you look at light, so first we'll draw this axis like this, CT x. Okay, what about light? We know that light always travels at the same speed, so you'll have x equal to ct. Okay, this is the trajectory taken by light, x equal to plus or minus ct. Right, you can just you know this, right? Because t is equal to x by c, or you can get it from the invariant interval. Right, you can get it from the invariant interval. D square is equal to c square dt square minus dx square. Right, for light we said that d square is 0. Okay, we said that if you take d square equal to 0, okay, we don't have to talk about light immediately. If you take this can be 0, right, this combination can be equal to 0. This is different from the Euclidean thing where it's dx square plus dy square, it's always positive. Right? In this case, positive or 0 it can be, but in this case it can also be 0 and 0 or negative. So when it becomes 0, you see that you get this equation, c square dt square equal to dx square. Okay, d square equal to 0 implies c square dt square equal to dx square, or we get a speed c square equal to dx square by dt square. We get an invariant speed, right? And this is c is equal to plus or minus, or we can write c dt. C dt is equal to plus or minus, or dx equal to plus or minus. We just take a square root on both sides. Right, c dt is equal to plus or minus dx. All right, or we can generally write x equal to plus or minus ct. Okay, so there is a particular trajectory given by this equation, and this equation is invariant because we just obtained it by taking a special case of this thing. This is invariant. All right, so there is this line, okay, and at this exactly at 45 degrees here. All right, this is the line corresponding to x equal to plus ct. Right, similarly you'll get the same line here corresponding to x equal to minus ct. Okay, these are two lines. All right, okay, and similarly if you can extrapolate it to the past also. All right, and this construction is known as a light cone. All right, so this is the locus of light cone, is a locus of all points for which are given by x equal to plus or minus ct. Okay, why do we call it a cone? We have only one axis here. If you include one more axis, you will see that it becomes a cone. All right, sorry, this is a light cone. This is known as a light cone. Okay, and this is known as a past light cone. You can call this as event A. Okay, this is known as the past light cone of event A. Past light cone of event A, and this is known as the future light cone of event A. Event A. All right, so these are the space-time diagrams. Okay, and what do we mean? So you see that the future is absolute for A. This is the absolute future of event A. All right, why do we say this is absolute future and this is absolute past? Okay, so we can see this. So this light beams, okay, we know that light happens to travel at this particular speed, or at the invariant speed in our space time, in our universe. is equal to the speed of light in vacuum. All right. Other than that, light has no importance. Light just happens to travel at this speed. Okay, at the maximum speed that can be admitted in our space-time. All right. Okay. So now, if you look at this, if you look at this ds square, right? We said that ds square has three possibilities. C square dt square minus ds square. Okay. There are three possibilities. One is ds square can be greater than 0 and such intervals. All right. If there are two events, and d square is greater than 0 between these two events. Okay, let's say this c and d. If d square is greater than 0, we say that these events are time-like separated. Okay, time-like separated. I'll explain this. So if d square is greater than 0, then you see that dt is greater than dx, right? dt square is greater than dx because this is greater than 0. So this has to be greater than this, right? So you see that the time part dominates in this combination. The time part dominates. That's why we call these events are time-like separated or time-like interval. If d square is greater than 0, we call the interval a time-like interval, or these events are time-like separated. Okay, and if d square is equal to 0, this is known as light-like because this corresponds to light. Okay, this corresponds to maximum speed in our space-time, and this is known as light-like. It's also known as null interval. Okay, light-like interval or null interval. Okay, and we also have a third possibility where d square is greater than 0. Sorry, is less than 0. Okay, these are space-like separation or space-like interval. Okay. Right. So what do we mean by time-like separation? Right? So if two events are time-like separated in any frame, right? So we know that this is invariant quantity, right? This is invariant quantity. Okay. So if d square is greater than 0 in any frame, then d square has to be greater than 0 for in all frames. It cannot change. All right. If d square is greater than 0, if two events are time-like separated in any frame, they are time-like separated in every frame. All right. This is always true. That's why we call this as the absolute future of A. This is an absolute thing. Okay. Corresponding to A, okay, all events inside this light cone are time-like separated. All right. All events inside this light cone are time-like separated from A. Okay. Are time-like separated from A. So all events in the future light cone of A are time-like separated from A. All right. So if you take two events inside a light cone, so I'm just going very quick here. But if you have any doubt, you can just ask. Okay. If you ask, it's easier for me to explain. So if you take any two events inside this, A and B, all right. So this is the light cone for one observer. Okay. If this observer will say that B happened after A, right? This is the time axis, right? So one observer will say that B happened after A, right? But since the time this ds, so for these two events, d square is greater than 0, they are time-like separated. So all observers will agree that B happened after A. So you see that there is in some way the causality is preserved. Okay. Causality means one observer says that B was caused by A, then all observers will agree. So the time order of the events inside the light cone cannot change for different observers. All right. So that's time-like separation, and so that's known as absolute future, etc. Okay. Now there are also space-like separated events. So one more thing. So we talked about time-like separated events. One more thing about this. Okay. Okay. These are two events which are time-like separated. It's inside the future light cone of, let's say, event A. Okay. This is absolute future. Why do we call absolute future? Because all observers, so all events in this light cone, right, are time-like separated from A. Right, are time-like separated from A, and all observers must agree. So all observers will agree that every event inside this are separated or is correspond to a future of A. Okay, all events inside this light cone are correspond to a future. It happens only in the future of A. Similarly, this is known as absolute past. Absolute past. because all events, every observer will agree that all events inside this past light cone happened before the event A. All right, this cannot be changed. All right, this cannot be changed. And so if two events are time-like separated, two events are time-like separated, okay, then you can find a frame. You can find a frame or coordinate system in which these events have take place. These events are at the same point in space. Okay, so we can always find an inertial system in which these two events are always in the same point in space. All right, but you can never find a coordinate system in which these events happen simultaneously. No, that doesn't happen. All right. So actually, since these light cones, okay, this light rays define the structure of space-time, you don't have to draw the coordinates anymore, right? So we just draw the light cone. You take a point in space-time, then you can always draw a light cone. Okay, no problem. Okay, so these two events, all right, these two events, they happen at different points in space. I'll just okay, I've taken one coordinate system CTX. You see that these two events happen at different points in space. Am I right? But there's always an observer who travels at a velocity speed less than c, for whom, okay, for this observer, these two events can takes place. So these two events take place exactly at the same point in space. Okay, let's call this observer O bar. For O bar, events E1 and E2 take place are event E1 and E2 are at the same point in space. Okay, there can only be conceptual questions from this. They may ask you to draw the space-time diagram or choose the correct space-time diagram. That's all. Okay. Okay. So that's thing. But never, there is no observer, but there is no observer for whom E1 and E2 take place simultaneously. Okay, so every observer will agree that E2 happened after E1. All right, E2 happened after E1. This cannot be changed. All right? This is if two events are time-like separated. Okay, I hope that idea is clear. Let's look at space-like separation. Okay, so one more thing I missed. Right. So if an event, okay, if an event A is there and you have a future light cone, okay, future light cone. This is the future light cone of A. These are events. So any event can be influenced in principle by A. Okay, because information can be passed from A to any point, okay, or any event in this space in the future light cone. Okay, in the future light cone. Right. So because you can just take so these events inside the future light cone of A can be causally connected to A. All right, A can what do you say, influence only the events inside the future light cone. All right. So if this is the speed of light, this if we take a point on the light cone, all right, or the light on this light cone, A can reach here to a light signal, all right? A photon starting on A can reach this point, all right? So all events in this can be causally influenced by A. But if you go to a point outside the light cone of A, all right? If you go to a point outside the light cone of A, there's no way that the event at A can influence the event B here, all right? Because you cannot pass information faster than the speed of light, right? So all the points connected to A with speeds less than c are inside this light cone. Okay, so in this case, there can be no causal connection, between B and A. All right. So no observer can say that B is caused by A. This is not possible because B is outside the future light cone of A. All right. This region is known as the elsewhere region corresponding to A. All right. This is okay. So that's one thing, because see, you can reach any event inside this light cone of A by traveling at different speeds. All right. If you travel at light speeds, at best you can reach an event on this line. All right. So no event can reach point. No, I mean no signal can reach from A to B. All right. So there cannot be influence. This is known as the elsewhere region corresponding to A. Okay. All right, now let's look at space-like separation. Right? Let's look at space-like separation. All right. So space-like separation, we said that ds square is less than 0. It's negative. Okay, which means that c square dt square minus dx square is less than 0. Okay, or in other words, c square dt square is less than dx square. Okay, so these regions, if you take A. Okay, this is the future light cone of A. All right. So all events outside the light cone of A. All right. All events outside the light cone of A. All events outside the light cone of A are space-like separated from A. Okay. This B, C, D. All these events are okay. All events outside. Okay. Past, future light cones of A, okay, are space-like separated. Okay, so these events which are space-like separated. Okay, so if you take two space-like separated events, all right, B and D. If you take two separated, so let's take E. Okay, these are two space-like separated events. All right, B and E outside the light. Or let's take A and B. Right, let's take A and B. These are two space-like separated events. All right. So if you take two space-like separated, this has been asked. Okay, which among the following is true? I don't think for net, but for some other examination. All right. So if two events are, I'll just write it down. If two events are space-like separated, then, okay, there is always a frame. There exists a frame. Okay, we mean inertial frame. We are talking about special relativity. Okay, there exists a frame in which these two events are simultaneous. Okay, we'll see this more clearly shortly. Okay, so if you take two time-like events, there's always a frame in which they happen at the same point in space. Okay, if you take two space-like separated events, there's always a frame in which these two events happen exactly at the same time. Okay, so you can even reverse the order of this. Right, so some observer will, so according to the observer that we are considering here, this will say that B happened after A. Right, B happened after A. There will be another observer who says that A and B happened simultaneously. There will be yet another observer who says that B happened before A. All these are possible. All right, there can be no causal connection between A and B. Also, we see that the future is unique. All right, the future of A is unique to A. The future of A is unique to A. If you take another point X, Y, if you take another point Y, it has a different future. It has a different future light cone. Okay, it has a different future light cone, but their futures can interlap. Okay, the futures can, intersect. The futures can intersect, right? But there are points where these futures cannot intersect also, right? So these are what we obtain as the structure of space-time, right? So there's always a frame in which these two events are simultaneous, all right? Light-like separated events. Okay, this just corresponds to the locus of all the points which can be connected by a light beam from the point A. Right? Light beam means light beam in vacuum, right? Light beam in vacuum. So these are the events which are connected to A by light beams, which can which start from point A. Okay, all these are like, now also if you look at the past light cone of A, okay, so only these events in the past light cone of A can have influenced A. Okay, so all these events in the past light cone could have influenced A, could be causally connected to A, but if there are some events outside this past light cone, okay, I'm running out of numbers here, Z, K, these events K and Z cannot have influenced A in any way, all right? They happened before A in some frame, but they cannot affect A in any way. They cannot have affected A in any way, all right? In the similar way, events outside the future light cone of A cannot be affected by what's happening at this point in space-time, all right? So is this clear? Now there's a small issue here. Okay, so we took ds square is c square dt square minus dx square. Okay, so you could also take ds square is equal to dx square minus c square dt square. Okay, so you have to look, if the question is given, you have to look which combination they have used. Both these are Lorentz invariant. All right, dx square. All right. So in this case, we said that if ds square is greater than 0, it's time-like separated. Okay, but in this case, they are time-like separated if ds square is less than 0. Okay, so don't get confused by this. Okay, so you just have to see which one dominates. Okay, so here you see that ds square is less than 0 if time dominates, or dt is greater than dx. Okay, or dt is greater than, sorry, c dt is greater than dx, etc. Okay, is this clear? Are there any clarification you need in this regard?
No, sir.
Okay, so some conceptual question can be asked from this. Okay. So let's look at now. That's about space-time separation. We have got time-like separated events, space-like separated events, and light-like separated events. All right. So you always remember that time-like separated events. You can expect a question in this regard. Okay. Time-like separated events can happen or can take place at same point in space for some observer. Okay, but never simultaneously. Okay, but simultaneously, they can happen simultaneously for no observer. Okay, so no observer can say that two events which are time-like separated happen simultaneously. Similarly, if you look at space-like separated events, okay, such events can take place simultaneously. Okay, we'll see this more clearly for some observer, but never at the same spatial point. Okay, I hope this is clear. These are the only kinds of things that can be asked, I think. All right. Now, another thing that has been asked for competitive exam is this question, all right? Which among the following, right? So, which among the following is the coordinates corresponding to a different observer, all right? So, we can draw the coordinates used by a different observer. So suppose this is the coordinates used by C, T, and X, right? The question is this: which among the following corresponds to a coordinate used by a different observer who is traveling at plus V, along positive x-axis, all right? So is this true? Ct prime. Okay, this is option 1, right? This is option 2. This is Ct x. This is Ct prime x prime. Okay, so option 2. Option 3 is this x Ct prime x prime. Okay, yeah, there are all sorts of options. Okay, you could also look at Ct x and x prime Ct prime. This is the 4th option. Okay, which one would you choose? Which one would you choose? Do you understand the question? These are space-time diagrams. Okay, so we know about rotations, right? In space rotation, we know that this is x, y. A rotated coordinate system would correspond to x prime, y prime. Am I right? Okay, so these are the new coordinate systems in the old coordinate system, right? In the same way we can do for Lorentz transformations also, for space-time diagrams also. Okay, so we talked about boost. So the question is this: suppose there is an observer. Okay, there is a frame, an observer, a reference frame, which is traveling at plus v. Okay, along or with velocity v along positive x-axis. Right now, how if this observer needs? So let me make the question more clear. All right, so you are the observer S. Okay, there is another observer S bar moves at velocity v along positive x-axis. Okay, all right, so which among the following represents the coordinates of S prime? Okay, let's say in the frame S. Okay, this is the question. I'll just just draw it more clearly. Okay, this is the question. I think this was asked maybe for GATE. I'm not sure if it's for NET, but such questions can be asked. Okay, now I'll give you the options. Okay, option A goes like this. This is the coordinate system S. Okay, we've got Ct bar and x bar. This is option A. Right, is this true? Or we have got option B, which corresponds to Ct prime x prime. This is x and Ct. Okay, and we have got option C, which looks like this. Okay, and we also have option D, which looks like this. Okay, so which option is true? Is the question clear? Is anyone listening still?
Yes, sir, listening.
Okay, which option would you choose? A, B, C, or D?
The question
Question is done, right? You have got a frame S with coordinates, unprimed coordinates. Okay, so the coordinates of S frame S are given by X and CT.
Okay.
Now there's another frame given by S prime. There's another frame given by S prime, which moves at a velocity v along the positive x-axis, all right, along the positive x-axis, right? Which among the following represents the coordinate of S prime in the frame S? Okay, it's just like doing this. We know about spatial rotations. We have got X and Y, right? So if you make a rotation in anti-clockwise direction about theta, you know that the new coordinates would look X prime, Y prime. Am I right?
Yes.
Because this orthogonality is conserved. This Y and X are orthogonal. The new Y and X are also orthogonal. The orthogonality is conserved under rotation. This is spatial. Okay, so you're asking the same thing for space-time. Okay, so this X prime, Y prime we have drawn in old coordinates. All right, how do X prime and Y prime look in the old coordinates, in the X, Y coordinates? That's what we have drawn here. Okay, in the same way, I'm asking you to draw corresponding to Lorentz transformation. Instead of spatial rotations, you have got Lorentz transformations. Okay, so I'm asking you this question. How do the new coordinates, the primed coordinates, look in the old coordinates, XCT? XCT are the old, so just like the spatial rotation thing. Which option is correct?
Maybe option B.
You say option B. Okay. Is there any other? Is anyone else trying to answer? Yes. I think I need your answers. Okay. All right, I'll tell you why option B is wrong. All right, I'll tell you why option B is wrong. Okay, just before some time I had given you a hint. Right, the time axis corresponds to the world line of the object which is at rest. Am I right? So if you look at the world line of, so I mean we can do this formally. I'll do this formally. All right. So if you take XCT, right, this is the world line of an object which is moving at speed v. All right. This is the world line of an object which is moving at speed v. So this is the world line of the frame S prime. Am I right? And we said that this world line corresponds to the time axis. Right. So an observer at rest in this frame. This is also the world line of the observer at rest in this frame. So this world line corresponds to the time axis. So this has to be a time axis, right? So it cannot be B. It could be A, C. It cannot also be D. It's either A or C.
A.
Pardon?
A.
A. Okay. So this is, I hope this is clear, right? Because I explained earlier. I took some time to explain that. Yeah?
Not a prayer.
ഇതൊന്നുകൂടെ പറയണോ? Right. കുറച്ച് മുമ്പ് പറഞ്ഞിരുന്നാൽ if you look at this frame, all right, I'll just draw here. If you look at this frame, CT X, all right, this CT axis, right, the CT axis is the world line of an observer who is at rest in this frame, right? So if you take an observer who is at rest at this point, X equal to, let's say 5, then the world line is just a straight line, am I right? He's moving only in time. Correct? Right? So the time axis coincides with the world line of an observer. There's an observer here, or there's an object here. The time axis coincides with the observer who is at rest in this frame. Am I right? All right? Correct? This I'm not taking any other observer. Okay, there are different world lines that you can construct, but you see that the time axis coincides with the world line of an observer of an object which is at rest. If you take an object at rest, so if you take the object at rest, object which is at rest at the origin, all right, object at rest at the origin, right, the world line is just a straight line. It's moving only in space. It's moving only in time. If it's moving in space also, its world line is like this, moving at the velocity v. Is this clear? Is this fine? So we are talking about the frame which is moving at velocity v. So that's the world line of this. All right, that's the world line of the object which is moving at velocity v. All right. Now, if you look at some observer in this frame, all right, the observer at rest in this new frame also has to be traveling at speed v. Am I right?
Yes.
Yeah. So if you are so just look at a train which is moving at speed v. All right. So the observer at rest in this frame is also moving at speed v. Am I right?
Yes.
Yeah. So we said that the world line of the observer who is at rest coincides with the time axis. Am I right? So the new time axis has to be this. It has to be the same as the world line of the frame, world line of the frame which is moving at speed v. That's the argument I'm trying to make. Okay. Right, but we can say this more formally. I'll do it more formally if it's difficult for you to imagine it. All right. So then the reason why you choose this answer, I know the reason why you choose this answer, because this seems to preserve the orthogonality. Am I right? Right. And then the next option that the other person choose, this also seems to preserve the orthogonality. Am I right?
Yes.
Okay. But this option, if you look at option C, this does not seem to preserve orthogonality. These are at 90 degrees, but this do not seem to be 90 degrees. Am I right? This also does not preserve orthogonality. Okay. I mean, it does not seem to preserve orthogonality. Right? But the mistake that you make here is that now you are thinking about orthogonality in Euclidean sense. Okay, but we are talking about a different kind of geometry where orthogonal does not exactly look the same. All right, we'll see this now. Right? These are orthogonal, all right, but these are orthogonal in a Lorentzian sense, not in a Euclidean sense. But this, if you cannot imagine all this, so let's just look at the transformation equations. Right, the transformation equations are given like this: Ct prime is equal to Ct cos phi minus x sin h phi, okay, and x prime is equal to minus Ct sin h phi plus x cos h phi. Okay, so now let's look at, these are the new time axis, and this is the new space axis. Am I right? Now, how do you find so if you have got y and x, right? How do you find the y-axis? You just take x equal to 0. Am I right? The line corresponding to x equal to 0 is the y-axis, and the line corresponding to y equal to 0 is the x-axis, right? X-axis corresponds to a line y equal to 0, and y-axis corresponds to a line x equal to 0. Is this correct?
Yes.
Okay. So here in the same way, we can look at the x prime, or let's first look at the Ct prime axis. Okay. The Ct prime axis. Okay. How do you find the Ct prime axis? You just set x prime equal to 0. Am I right? It's in the just in the same way, because we have got Ct and x. If you take x equal to 0, you get the Ct axis, right? Or the time axis, right? So you just set x equal to 0, and then you get the equation of the line corresponding to this thing. All right. So if you take x prime equal to 0, you see that this corresponds to the line Ct sin h phi is equal to x cos h phi. Okay. Or Ct is equal to, let's write it like this, x by tan h phi. All right. Is this correct? Or we can also write it Ct is equal to x cot h phi. All right. This is fine. Now, if you look at this, this looks like the equation y equal to mx plus c, right? Am I right? This is correct.
Y is equal to mx plus c, straight line equation.
Where c is the 0. It's a straight line, right? Straight line passing through the origin because c is 0.
Okay.
Right? So this is a straight line passing through the origin. So if you look at this equation, Ct and x, you have a straight line passing through the origin, and this gives the slope. Okay. So this is the Ct prime axis. Okay, because CT prime axis corresponds to x prime equal to 0, and that's an equation of straight line. CT equal to x cot h phi, and it has a slope given by what do you say, a tan h phi or cot h phi, okay, depending on slope with respect to which. All right, is this clear? So if you take the slope of this, if you take it as CT and x, you see that CT by x equal to cot h phi. All right, this has a slope cot h phi. Is this clear? So this is the CT prime axis. Is this fine?
Yes.
Okay, now we need to find the x prime axis. So in order to find the x prime axis, you just put CT prime equal to 0. Am I right? So if you take CT prime equal to 0, I'll write it here. If you take CT prime equal to 0, you see that the equation corresponding to it, x prime axis corresponds to CT prime equal to 0. This means that this is the equation given by CT cos h phi is equal to x sin h phi, okay, or CT is equal to x tan h phi, right? X tan h phi, right? So we see that this has exactly the same slope only with respect to the other axis, all right? So this is CT. You see that CT, this is also a straight line, right? This is also straight line. You see that this is also straight line, y is equal to mx plus c, where this is the slope, tan h phi, right? And tan h phi is equal to CT by x, or x by CT is equal to tan h phi. You see that this line corresponds to a straight line which goes like this. Okay, if you draw it, you'll see that this is, because it's exactly the same slope. Okay, this slope is CT by x. If you take CT by x, here you see that CT divided by x is equal to CT divided by x equal to, or here you see that, or let's put it like this. You see here, in this case, you see that x equal to CT tan h phi, or you see that, yeah, you can say this is the slope, tan h phi is equal to x divided by CT, right? So you can say this is the slope, tan h phi is the slope with respect to the x-axis. You can say that tan h phi is the slope with respect to the x-axis, okay? So that's why we have it like this. And here you have tan h phi is the slope with respect to CT axis, right? Here tan h phi is equal to x by CT. Here you see that tan h phi is equal to CT by x. They are symmetric, right? Okay. So these angles must be the same. We will call this as alpha. Okay. So these are the new coordinate systems. Right? These are the new coordinate system. Is this clear? This have to be exactly the same, right? Because here you see that CT prime by x equal to CT prime, CT by x. Okay, you see that CT by x equal to 1 by tan h phi. Okay, and it's exactly the mirror of this, because here CT by x equal to 1 by tan h phi, right? Like that. Is this clear?
Okay.
These both are straight lines with exactly the same numerical slope with respect to different axes. Okay, this is the slope, tan h phi is with respect to CT axis. In this case, it's with respect to the x axis. That's all. The slope is exactly the same. Okay, so the option, the correct answer would be this one. Right, this is the correct option. And they don't look symmetric. You see that this axis, when you make a Lorentz transformation, they are scissored together. Okay, they are scissored together. Okay, but you see that this conserves orthogonality in a Lorentzian sense. We may not go into detail there. So this is orthogonal in a Lorentzian sense. These are orthogonal in a Lorentzian sense. Okay. Now, if this is not clear, you just look at these equations and imagine how this equation has to be, and you'll see that this is the correct answer. And you'll see that, again, you'll see that the speed of light, x equal to CT, corresponds to this line at 45 degrees. And this is also x equal to CT. This also equals to x prime equal to CT prime. Right? Both these are the same line. This means that the speed of light is invariant in all reference. Okay. Similarly, if it's moving in minus v, okay, it moves with the velocity v along the minus x direction. Right?